Number 28. A car engine moves a piston with a circular cross-section of 7.5 plus or minus 0.002 centimeters in diameter, a distance of 3.25 plus or minus 0.001 centimeters to compress the gas in the cylinder. So A, by what amount is the gas decreased in volume in cubic centimeters? All right, so first thing is, let's just sketch a rough picture here. So over on the left-hand side, I'm going to do so. So we have this cylinder that's basically like a piston. So we draw this. Okay, now it tells us that the cross-section's diameter, right? So I'm going to draw the diameter here. So the cross-section's diameter is, draw a little arrow, is 7.500 plus or minus 0.002 centimeters. Okay. And it also tells us that this piston, or that the circular cross-section is going to be compressed, right? We're going to push down on it, and it's going to move this value, right? 3.25 plus or minus 0.001 centimeters. Okay, so let me draw that in here. So eventually it's going to reposition itself somewhere down here. Okay, and it moves the distance as I just mentioned, 3.250 plus or minus 0.001 centimeter. Okay, great. So now it wants to know by what amount is the gas decreased in volume. Okay, so the first thing is we have to recognize that we're dealing with a cylinder. Remember, it says it in the problem there. Okay, so what's the, if you recall the formula, for volume of a cylinder, it will be V is equal to pi r squared multiplied by the height. Okay, so we need to know, in order to find the volume, we need to know the radius of the cross-section and the height. All right, so just so that we're clear, this is basically the cylinder that we're talking about. So from this point down to here, okay, that's going to be our cylinder. So our height value is in gold here, right? That's going to be the height. And they didn't tell us the radius, right? They told us the diameter of the cross-section, but that's not a big deal, right? We know we have to take the diameter and then divide it by 2. Does that make sense? Okay, so let's now plug in those values. All right, so the volume is equal to pi multiplied by the radius, which, remember, the diameter was 7.500, and I'm just going to divide that by 2 so that I find the radius, and that value will be squared, and then multiply it by the height, right? So that was 3.250. I just left out the units here, but they're both in centimeters, right? So that's good. I have to make sure that they're consistent, which they are. Okay. So now let's just take this and plug it into the calculator. So we're going to do pi times 7.5. Actually, use parentheses if you're going to do this all in one step. So parentheses 7.5 divided by 2. Close the parenthesis and then square that. And then multiply it by 3.25. Okay, so the value works out to be about 143.58. And that's centimeters cubed. Now we have to always consider significant figures. So it appears that this value here, right, has 4. This value here has 4. So our answer will have 4 sig figs. Now remember, I know that this number has 1 sig fig technically, but that's not a measured number, right? It's a number that I had to divide a measured value by in order to find the radius. So that won't count in terms of significant figures. Remember, we only care about significant figures for measured values. Okay, so we have to round here to 4 sig figs, so this will become 143.6 centimeters cubed. And that's the answer to part A. So now we have to find the uncertainty in this volume. Now remember, since we had to do a calculation in order to find the volume, we're going to then, if we want to find the total uncertainty in this calculation, we want to think about it in terms of percent uncertainties. Okay, so recall this formula, that total percent uncertainty is equal to the percent uncertainty of the first value used in the calculation plus the percent uncertainty of the second value used in the calculation plus the percent uncertainty of the third value used in the calculation, blah, 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 blah. Okay, so what values did we use in the calculation of the volume? Well, go back to the picture. We used the diameter value, which we converted into the radius, and we also used the height, right? So those were the values. Now, we used two values, but be careful, we really used the radius twice, right? What do I mean by that? So focus on this part here, right? Really what I did in terms of the calculation, or if we were to think about how we multiplied these numbers together, I can rewrite that equation to look like V is equal to pi multiplied by 7.5 over 2. Now, just to make this easier, let's just do that division. Okay, so that number works out to 3.75. So I really took 3.750 times 3.750 and then times 3.250. So although I used two measurements, I really calculated three measured values in the formula, right? 1, 2, and 3. So going back to the total percent uncertainty formula, remember, in order to find the total percent uncertainty, we have to find the percent uncertainty in the first measurement of the first measured value that we use in our calculations, plus the percent uncertainty of the second value that we use in our calculations, plus the third, plus the fourth, plus the fifth, etc. Okay, so basically, right, each one of these values I need to find the percent uncertainty for. Okay, so first let's talk about finding the percent uncertainty with respect to the radius. Okay, so let's write that over here. So percent, uncertainty of the radius will be equal to the uncertainty of the radius divided by the measurement of the actual radius multiplied by 100. Now remember that the diameter was 7.500 plus or minus 0.002, right? And in order to find that was the diameter. And now in order to find the radius, I had to divide this value by 2. But in order to, not only did I divide or needed to divide this magnitude value, I also have to divide the uncertainty by 2 as well. So therefore, when I write the radius, it should look something like this. Now, with its associated uncertainty, it should be 3.750 plus or minus 0.001 will equal now the radius. Okay, and that should make sense, right? If you think about right, the uncertainty when you measured the diameter should be larger than if you were to measure the radius, okay, because it's a longer measurement. So now, this is really the value that I'm considering when I'm talking about the radius. Its measured value with its associated uncertainty. So, to find the percent uncertainty of the radius, we need to find the uncertainty associated with the radius, which we calculate to be 0.001. Divide that by the measured value of the radius, which was 3.750. Multiplied by 100. Okay, so now we just gotta, or have to plug this into the calculator, so the uncertainty of the radius. So take 0.001, divide it by 3.75, and that works out to become 2.67, right? 2.67 times 10 to the negative 4. Oops, and don't forget to multiply by 100, so it should just be to the minus 2. Let me just backtrack. So it should be to the minus 2%. Now go back and look at your calculation. There's only one significant figure there in the numerator, so therefore my answer cannot have more than one significant figure. So the percent uncertainty associated with the radius should be equal to 3 times 10 to the negative 2%. Okay. Now remember, we used the radius twice in our calculations, right? We use it twice right there as I boxed it in. So this percent uncertainty, let me just change the color. This percent uncertainty is going to be for the first measurement value and also for the second here in our formula. Now the third one that we use in our calculations is the now height. So that's the next job. That's my next step. I have to find the percent uncertainty now, percent uncertainty associated with the height. And remember, that should be equal to the uncertainty of the height measurement divided by the measurement of the height itself multiplied by 100. So the percent uncertainty associated with the height should be equal to the uncertainty of the height, which they told us, right? If we go back to the problem, here it is. This is the measured value of the height with its associated uncertainty. So the uncertainty there is 0.001 divided by 3.250 multiplied by 100. And both units are in centimeters, so they will cancel, right? And my percent will essentially be unit less, which it should be. So let's just pull out the calculator, 0.001 divided by 3.250. So the value comes out to be approximately 3.077 or so, right, times 10 to the negative 2%. But again, only one significant figure there in the numerator. Therefore, my answer cannot have more than 1, and this works out to be 3%. Not 3%, 3 times 10 to the minus 2%. Okay. Now, this should kind of make sense, right? I'm assuming that they're using the same tool to measure both the diameter and therefore the radius and the height. Notice how the height and the radius value, I'm going to circle them. Here's my radius value. Here's my height value. Notice how they're very close to one another. So if they're very close, their percent uncertainty should also be very close, in which they are. That should make sense, right? Okay. So now we have the third value that we need. So we can plug that on in. Okay. So now, great. I can now finally find the total percent uncertainty of the measurement of the volume calculation, that is. So this is just 3 times 10 to the minus 2 plus 3 times 10 to the minus 2 plus 3 times 10 to the minus 2. So now the total percent uncertainty will work out to be 9 times 10 to the minus 2. So just plug that into the calculator, right? And you should arrive at that same value. And that's in terms of percent. So that's the total percent uncertainty. Now remember, they didn't ask for the total percent uncertainty. They said find the uncertainty. So we just have to do one more step, okay? What I'm now going to do is I'm going to take my measured volume value and its associated percent uncertainty and basically put them together. So I'll do that here at the bottom. So basically I could write this, 143.6 centimeters cubed, right? Plus or minus 9 times 10 to the minus 2%. Now that would be fine if they wanted it in percent uncertainty, but they don't. They want to find the uncertainty. So what we need to do is we need to take this percent uncertainty and just convert it into the uncertainty in the measurement. So how do we do that? Well, we've basically been doing that for the past 2 steps. Think about the formula, right? I'm going to write it up here below the problem. So we have now our percent uncertainty is equal to the uncertainty of the measurement divided by the measurement itself, right? Multiplied by 100. So the percent uncertainty we just calculated, it was 9 times 10 to the minus 2. The uncertainty is what we're trying to find, so that's our variable. And the measured value was 143.6. Multiply that by 100. Now simply solve this, just do the math and solve for the uncertainty. So 9 times 10 to the minus 2 multiplied by 143.6 and then divide out the 100. Okay, so this works out to be the uncertainty here in this measurement is now going to be, hold on one second. Great, so this one works out to be 0.129, etc. Okay, Now, only one significant figure in your calculation here, so therefore my answer cannot have more than 1. So the uncertainty here would be equal to 0.1. Okay? So that's now the answer. That would be the answer for letter B. Okay? And let's just rewrite how this will now look with the volume and its associated uncertainty. I'm going to do that in the upper right-hand corner. So it'd be 143.6 centimeter cubed. And actually, I should have put the units in here. So let me just erase over here. Don't forget the units. This is in centimeters cubed. And then it would be plus or minus 0.1 centimeter cubed. And that would now be the measurement with its associated uncertainty. And notice a quick check is to notice where the measurement goes out. The measurement goes out to the 10ths place. And my uncertainty also goes out to the 10ths place. That should be consistent. If they're not, something went wrong in your calculations. So that's a good check. All right, guys, if this helped you out at all, please do subscribe. It would mean actually a lot to us. Thank you so much.